Hello everyone. Hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of unit number 6 entitled as GIS data representation and its applications. So, GIS data is broadly classified into spatial and non-spatial data, which is used to represent real-world features. So, objective behind that is we have to accurately model the geographic features for analysis and decision-making process. So, the data is stored as a grid cells. We can see that raster, or in terms of points, lines, polygons, like vectors. So raster and vector, there are two working principles of data representation, which will be the GIS data. So the spatial accuracy, scalability, layer-based organization, these are the characteristics of GIS data, where in civil engineering domain, that GIS data is used for mapping the roads, drainage systems, land parcels, etc. It is also helpful for visualization and planning of infrastructure projects efficiently and effectively. So data representation is nothing but how to present the actual scenario in the form of abstraction. Today, how we can represent our physical world in digital GIS environment, we have to see the picture, the actual real world intersection of road, which will be enhanced in the GIS view by using some attributes. As civil engineers, we are the creators who transit from traditional surveying real world activities or landscapes to building the digital models that inform our designs or that reforms our designs. We will also convert the geographic data, which will be structured format with respect to the various ways that acquire the information from GPS to remote sensing, and that critical process is also known as georeferencing. So the GIS data representation is based on the georeferencing, or we can take the base of georeferencing for the attribute presentation or updating the models or real world applications. So mastering these fundamentals ensures that our whole project data must be accurate, must be consistent, and ready for advanced spatial analysis. We can use that data as an input for training the model so that the modeling reality is most important point with respect to the GIS data representation, where entity versus object comparison is there. So entity is nothing but a real world phenomena where digital database representation is an object. The process behind that, or the process which will follow, where real world application is converted, or real world data is converted into the digital database, real world to the data model and digital database. So data model is used to change the reality in the GIS view. So in civil engineering context, converting physical survey sites or converting the traditional survey sites landscapes into digital terrain models, that is DTM, is the main objective. The concept of GIS data representation, which is based on the two types of data representation, raster and vector. So the data representation is the method by which we can simplify the complexity of the earth, which is a geodetic curvature, or which is geodetic earth, or the curvature of the earth is considered with respect to its features which are inbuilt or associated on the surface, like its curvature, into a computer readable format. So in GIS, we represent geography as a series of layers, each layer focusing on a specific theme like road layer, topographical layer, utility layers, etc. So for a civil engineer, this allows us to stack information to see how a new highway project or new highway alignment might intersect with existing water lines, existing sewage treatment lines, or any geological fault planes or lines. Likewise, we can compare. By organizing that data into discrete layers, we can perform the complex multiple criteria analysis where more efficiently and traditional paper planes are to be constructed or are to be updated by using that grid or coordinate system. So grid model is a raster model and coordinate model is a vector model. So the structure of raster model, which is based on the grid of cells or pixels. These all cells are quantized with respect to the space in between them, like equal space in between them. These raster models or grid models are most suitable for the use of continuous fields like elevation, satellite imagery, etc. But one more point is that limitation where large storage is required for storing the activity which will be completed by the raster data or the grid model. So that in vector model, we can see comparatively, which is based on the positioning system basically, that is a coordinate system. The structure of vector model is a coordinate base like XY axis where continuous space is captured or continuous data will be collected. By using that, we can monitor the whole irregular shapes also or regular shapes also, which is the best suitable for discrete features like property lines, pipelines, etc. The main advantage of the vector model is that compact storage and maintains topology or maintains topographic activities, nothing to be changed or nothing to be required to be changed on existing Earth surface. Now, coming towards data acquisition methods, or we can say that the data stream, basically the flow or the path of data acquisition. Data acquisition is nothing but a process where we have to collect the database based on that primary data or secondary data, which are the two types of data. Primary data, which is the direct measurement by using GPS tool or by using satellite, so that the whole primary data is directly saved or stored at any place or in any device. And secondary data is the digitizing or scanning of existing paper maps. Just we can say that the updating the existing maps or updating the previous topo sheets by the Survey of India department or likewise departments. So the data acquisition is nothing but a process of collecting spatial and attribute data from various sources. Keeping the objective is that to gather accurate and reliable geospatial data. So data is obtained using GPS, remote sensing tool, total station, DGPS, or any type of surveys as a working principle for acquisition. Or we can say that the method of acquisition. So the accuracy is on a higher scale, real-time capability is there, multiple data sources are utilized. So that these are the all characteristics for data acquisition. Where civil engineering application point of view, we can say that this data acquisition method is most important for essential site surveys, alignment design, and construction planning. It ensures that the better decision-making procedure in engineering projects, which is more crucial. So the analog sources are the input, existing maps are the input, or tabulated attribute data or vector data is also the one of the input. So with respect to that input, direct digital process is there, then the satellite user connectivity is there, or any tabulated data or any type of row and column is selected by the any user as a process. So in that procedure, scanning and manual digitizing is there. In direct digital process, remote sensing and field surveys are used for the satellite imagery by using the user on their cell phone or in their controller panel like this. Or we can change or any update any entry by using the keyboard in the vector tabulated format. So basically these three comes integratedly to form the GIS database. That GIS database is a more useful term for updating, for minimizing the efforts and many more activities. The GPS data is collected by using the three main basic segments. Three segments are nothing but a triangulation procedure. So we are studying the concept of GPS data collection, which is an important component of remote sensing and GIS application in civil engineering. GIS helps in collecting accurate geographic coordinates for mapping, surveying, and infrastructure planning procedures. These three segments are space segment, control segment, and user segment. So the space segment is, is a constellation of more than 24 satellites which are transmitting the signals continuously for the positioning the signals to the Earth. Then, second is the control segment, which includes the ground monitoring stations that track satellite health, orbital positions, and timing accuracy. These stations ensures that the reliable signal transmission and maintain the precision required for civil engineering surveys and GIS database. The user segment, which is a VR users or consumers, refers to the GPS receivers used by surveyors or any type of engineers on the field. These receivers calculate the exact ground position using triangulation or trilateration methods based on signals received from satellites. So for obtaining the accurate 3D or three-dimensional coordinates like X, Y, and Z coordinate, at least 4 satellites are required for that procedure. It enables determination of latitude, longitude, elevation, and timing information, which is more necessary for topographic mapping and construction activities. So in civil engineering, we can say that high accuracy GPS is widely used for establishing ground control points, road alignment surveys, dam monitoring, and GIS-based infrastructure development. Moving towards the georeferencing concept, which is the building block material, or we can say that building block concept for the GIS data representation or updation. So georeferencing assigns real world coordinates to maps or any type of images. So definition of georeferencing is assigning real world coordinates to a raster image. So what is the objective behind the georeferencing? To align spatial data with Earth's coordinate system. So control points are used to match map features with known coordinates, which is the working principle of georeferencing concept. So the accuracy depends on control points and transformation methods, which is the most important characteristics for that, where civil engineering, land records department, mapping and zoning in town planning, overlay analysis of various layers, which is enables the integration of multiple data sets in GIS by using the georeferencing concept. So we have to superimpose any satellite image or any raster image on the existing topo sheet. With respect to that, we can check the displacement and the mechanism which is based on the ground control points. That ground control points suggest us that the changes or updation required. So the georeferencing is nothing but assigning of real-world geographic coordinates to a dataset, such as scan maps or satellite images. Without georeferencing, a digital image is just a collection of pixels. I repeat, without georeferencing, a digital image is just a collection of pixels with no spatial meaning. So we have to collect the data of spatial meaning. By identifying that, ground control points are most important to assign the locations which are visible on the image with known coordinates like X, Y. That data which is associated or situated or marked on the Earth surface, on the Earth curvature. For civil engineers, this allows us to overlay an old site plan onto current satellite imagery to identify changes in the landscape over time. So time zone is most important point for the georeferencing point of view. In the next map projection system, we can say that the map projection is the mathematical transformation of curved earth to flat plane. Means we have to consider the earth is a plane surface or 2D surface. Basically, the earth is a 3D plane. So earth, which is in spherical shape, we have to convert or we have to consider that whole earth in a projection phase, just like a cylindrical phase, where the whole cylinder is divided into n number of blocks which have rows and column R1 and C1 likewise format. So this whole cylindrical earth is converted into a plane, and that geographic system which shows that the latitude and longitude in terms of degree, minutes, and seconds, so that we can take the ground control points for our reference and for our updating the procedure. So universal transverse Mercator or the Cartesian coordinate system, which is in meters, is used for the projected system for map projection. We can project any single cell from any topo sheet or from any Earth's curvature on a large scale. So every projection distorts shape, area, distance, direction, just like the characteristics. So with respect to the civil engineering domain, if we are surveyor or if we have to do the survey, then conformal projections like universal transverse Mercator perceive the local shapes, and we can use that for the projecting the activities. Now, accuracy in the GIS data. Why we are doing the survey? Because we want high precision and high accuracy. But sometimes we can't get that objective or we can't get that outcome effectively. So our actual ground control point or actual location is somewhat any point, and our whole accuracy or our whole GPS data or satellite imagery showing the actual point somewhat nearby. So there are some errors. So error types in safety, or in terms of that error, we have to remove that error, or we have to normalize that error with respect to the high precision and high accuracy. So basically, three types of errors: positional errors, attribute errors, and topological errors. Why these three errors are there? Basically, if we are digitizing the topo sheet, digitization is the process of converting features from georeference raster images like scan maps into vector points, lines, polygons, etc. So with respect to that point, line, and polygon, we have high precision and high accuracy pointing down control points. So positional error, which is a coordinate displacement or the change in position of some meters or some in kilometers. So coordinate displacement in XY offset. In terms of attribute point of view, attribute errors are there: incorrect labeling or any incorrect data entry, which will be a manual error also. In topological error, unclosed polygons, overshoots, and undershoots. These are all the parts of topological errors. So what are the sources to maintain the accuracy, or we have to improve the accuracy in GIS data? That instrument limitations, processing errors, human digitizing mistakes. Error detection and correction is most important point to integrate the accuracy in GIS data, which is essential for maintaining the data integrity. So data integrity, or we can say that data safety, is most important based on that accuracy, based on that characteristics, based on that precision level. So what are the applications of GIS data in surveying or over traditional surveying or in civil engineering? So that with respect to the route alignment, with respect to the watershed analysis, everywhere we can use that concept based on the layer, based on some plane, based on some ground control points, or based on some mapping, etc. So in the route alignment, optimizing the highway or railway paths using cost reference analysis, where slope and land use layers are comparatively checked and analyzed. In hydrology, we can say that the watershed analysis deriving drainage networks and catchment areas from the digital elevation models. In cadastral mapping also, the precise vector management of property, boundaries, and land records department also use that GIS data application. And in the soil, vegetation, and slope, sites suitability, we can check for any dam catchment or any construction project, overlaying soil, vegetation, and slope layers for construction planning. Stay tuned, guys. Happy learning.